Hello and welcome to the Radiation Basics Training. My name is Armin Ansari. I'm a health physicist at the Centers for Disease Control and Prevention. Now, if you're participating in this training, you may be a public health professional, a clinician, a law enforcement official, a first responder, or someone who wants to know more about radiation and radioactivity. And you are in the right place. Now, the word radiation carries a negative connotation for many of us. It's not something we want in our lives generally. But the truth is that radiation is all around us every day. We're exposed to radiation constantly, from radiation that comes to us from outer space, elements in the ground, the food we eat, and the air we breathe. And these everyday exposures don't do us any harm because our cells and our bodies have evolved and adapted to living in these conditions just like any other life form on Earth. So it's important to keep this context in mind as we explore and evaluate additional exposures to radiation. Now, this training gives you a basic understanding of radiation and radioactivity and prepares you for more advanced training. Radiation Basics is divided into 8 segments. In these segments, we will discuss sources of radiation, radioactive decay, measuring radiation, biological effects of radiation, radiation protection, decontamination. Let's get started. Now, in this training, whenever we talk about radiation, we're really talking about ionizing radiation. So let me first describe to you what radiation is, and then tell you what's different about ionizing radiation. Radiation means energy that originates from a source and then travels through space at the speed of light. And this energy has an electric field and a magnetic field associated with it, and it has wave-like properties. So a more technical term for it would be electromagnetic wave, but we just call it radiation. The most familiar form of radiation is actually visible light. Visible light is electromagnetic waves. It's energy that originates from a source and travels through space at the speed of light. It has wavelengths and frequencies that defines its energy. And if we're blessed with good vision, we can actually see this radiation. We can detect it with our eyes and see this radiation. And the difference between colors of light, red, green, blue, and so forth, is in their energy, wavelength. That's what sets them apart, and that's how we can detect them. So different colors of light are actually radiation of different energies that we can see. Now, the spectrum of visible light that we see, the range of visible light, the different colors, is only a tiny fraction of the entire spectrum of electromagnetic radiation in nature. The nature has radiation with energies that are far less and are far higher than visible light. So if we start in the range that we can see, and start with red, which has the lowest energy. Red light has lower energy than blue light. So let's say we start with red and go down in energy. We go to infrared, microwaves, radiation from cell phones, radio waves. These are all forms of radiation that have less energy than visible light, and of course they're invisible to us. Now, if we go higher energy, let's start again, come back to the visible spectrum, and go to blue light, which has a higher energy, and then purple. Then we go to ultraviolet, and X-rays, and gamma rays. And these types of radiation have much, much higher energies than visible light. And of course we can't see them. But we have detectors, instruments that can detect these types of radiation, and in other segments I'm going to show you how we do that. But we have instruments that can detect these types of radiation. Just like we have instruments that we can measure the intensity of visible light. We have light meters that do that. We can detect it with our eyes, of course. And then radios. Radios, we can tune into frequencies in the radio frequency and do that. So we have instruments to detect all types of radiation. In fact, it's interesting because at any moment, all the radiation signals that carry information for all our favorite radio stations and television stations are all here in this room. It's just a matter of having the right instrument to tune into it. I want to talk about ionizing radiation, which is X-rays and gamma rays. So what happens at the higher energy side of the electromagnetic spectrum, these forms of radiation interact with matter. They have enough energy to remove an electron from an atom. And when they do that, the atom becomes charged or ionized. So that's why we call these ionizing radiation, because they have a capability to ionize atoms when they interact with them. This is a unique property That is, these other forms of radiation, including what we get out of a cell phone, don't do that. So in this training, we're going to focus exclusively on ionizing radiation. Even though we might just say radiation for simplicity, what we really mean is ionizing radiation. So where does ionizing radiation come from? Well, in our nature, ionizing radiation comes from radioactive atoms. And radioactive atoms, just like any other atom, as you know, are building blocks of matter. So it could come in solid form, it could come in the form of gas, like this, or liquid. So just like any other matter, radioactive material or radioactive atoms are part of matter. They could come in gas, liquid, or solid. But what makes an atom radioactive? As you know, atoms are composed of a nucleus and have a cloud of electrons that surround them. In the nucleus, we have protons and neutrons. And there needs to be a good balance between protons and neutrons for the atom to feel stable. Let's take carbon, for example. Now, carbon has 6 protons and 6 neutrons. And that's a pretty happy carbon atom because it's pretty stable. Proton determines what the identity of the atom is. So if you take the carbon atom and we add an additional proton, 7, it's no longer carbon. It becomes nitrogen. Nitrogen has 7 protons. And nitrogen likes to have 7 neutrons to be happy and stable. Often you see in this training also, we would follow the name of the element with a number. Say nitrogen 14 or carbon 12. That number is the atomic mass number, is a summation of protons and neutrons, the sum of protons and neutrons. So that number, that's what it refers to. So nitrogen with 7 protons and 7 neutrons is a stable nitrogen. Nitrogen 14 is happy. Carbon 6 and 6 is a stable carbon atom. But carbon 14, which we see in nature and we'll talk about later, has 6 protons, which makes it carbon, but 8 neutrons. So it has 2 additional neutrons, and that's an unstable nucleus. And it's radioactive because unstable nucleus doesn't like to remain unstable. It likes to reach a more stable state. And what it does is eject some of that extra energy, ejects it out to reach a more stable state. And this process I just described is radioactivity. So let's discuss some key terms. Radioactivity, then, is the spontaneous release of energy from an unstable atom. Radioactive material could be a solid, liquid, or gas that contains radioactive atoms. And radiation is the energy that comes out of the radioactive atom. Radioactive isotopes, and sometimes we call that radionuclides, are radioactive atoms of the same element that they have different numbers of neutrons. An example would be iodine. Iodine 131 or iodine 125. Now these are both iodine, element is iodine, but they have different number of neutrons and they're both radioactive. So we call these radionuclides or radioactive isotopes. And then radioactive decay is that process, the change, going from an unstable atom to a more stable atom by emitting radiation. So the carbon-14 that I mentioned earlier, the carbon-14 atom would go through a radioactive decay process, expel some of that extra energy, and change back to a nitrogen-14. So carbon-14 will go to nitrogen-14, which is a more stable atom. Uranium, also we find in nature, uranium would go through radioactive decay process and transform into an atom of thorium, which is a more stable atom. But sometimes even the atom that it transforms into still needs to go through more processes. So thorium is still radioactive, has less energy than uranium, but it still needs to go through a few steps of radioactive decay. So I'm talking about now a lot of different types of radionuclide, uranium, thorium, carbon, nitrogen. We actually have quite a lot of radioactive material in our environment that occur actually naturally. Most of them occur naturally. One group of radioactive atoms, we call them primordial. These atoms were around when the solar system and the planets were formed. These include uranium, thorium, and potassium. So they were around, what we find today, they were around when the planet was formed. I want to talk about potassium a little bit because all of us know about potassium. Potassium-40 is radioactive, but potassium-39 is the stable one. Stable potassium has 19 protons and 20 neutrons. That's the balance of proton and neutron that makes it happy. So a potassium with the number 39, that's the stable. And out of every 10,000 potassium atoms we found in nature, 9,999 are potassium-39. But 1 in 10,000 has an extra neutron, which makes it potassium-40. And that is a radioactive potassium because it's a little bit unstable. So it needs to get rid of that extra energy to become more stable. Now, potassium-40 happens to be a patient atom because it takes it about 1 billion years to do that on average. The half-life of potassium, we'll talk about half-life later, but it takes it more than 1 billion years to go through that transition and become more stable atom. Now, some of our foods, I'm sure many of you like bananas. As you know, banana is rich in potassium. Anything that has potassium, it also has potassium-40. Because out of 10,000 atoms, one of them is potassium-40. So we have actually plenty of potassium-40 atoms right here in these bananas that we eat. Our bodies, we have potassium in our bodies, and we have potassium-40 in our bodies. And we can actually measure the radiation that we emit because of that. The other group of radionuclides we have in our nature, we call them cosmogenic. And that means that when we have cosmic rays coming to us from outer space, these cosmic rays interact with atoms we have in our environment, particularly in our atmosphere. And they create new species of radioactive material. A good example, we have plenty of nitrogen in our atmosphere. And cosmic rays interact with nitrogen and make carbon-14. Remember, carbon-14 is a radioactive carbon. Carbon-12 is a stable one. So carbon-14 is generated in our atmosphere when cosmic rays from outer space interact with nitrogen in our atmosphere. And this carbon-14 over time becomes part of our nature, incorporated in our environment, and becomes part of every organic life on Earth. We all are carbon-based. That means we have carbon. In fact, 1 out of every trillion carbon atoms is a radioactive carbon. So we have carbon-14 in our bodies and anything else that's organic. Now, you're familiar with carbon dating. That's based on this principle. The reason we can do carbon dating is because anything that has carbon in it, we know has carbon-14 in it, and we know the half-life, and we can estimate the approximate age of whatever it is that has carbon as part of it. The last group of radionuclide I want to talk about, they're called man-made. We call them man-made because, as the name implies, man-made them. They're through human activities that we have them in nature. One example of that would be cesium-137. Cesium-137 does not occur naturally in our environment. It's actually a byproduct of nuclear fission. And the cesium-137 that we find in our environment are remnants of atmospheric testing of nuclear weapons in the 1950s and 60s. Cesium-137 was part of that nuclear fallout, and now we have it, it has become part of our environment. Small amounts have become part of our environment. We use this knowledge of how to produce new species of radioactive material actually to our benefit too, because many of the man-made radionuclides we produce today are intentional because they have either applications in medicine, industry, or research. Another man-made source of radiation I should mention is those that are machine-generated. They don't come from radioactive materials, they're machine-generated, and you all know about them. X-ray machines and CT scanners. In those machines, there's no radioactivity, but they use electricity to generate ionizing radiation. But once they generate it, those ionizing radiations have the same properties as the ionizing radiation that we get naturally from radioactive material. But the generation is through a different mechanism, and there's no radioactivity involved in there. So now we're talking about lots of stuff, lots of radioactive material, lots of radiation coming from everywhere. So the question, how much are we getting from all of these sources? What we call the amount of radiation is the dose. And we measure it in units of millisieverts. In the United States, an average person receives 3 millisieverts of radiation from natural sources, from the cosmic rays, the ground, the food, and everything. 3 millisieverts. Of that 3 millisieverts, 2/3 of it, on average, comes from radon. Radon is a radioactive gas that occurs naturally and has its origin actually to the uranium in soil, the breakdown of uranium in soil. So it's a naturally occurring radioactive material that is in form of gas. So when I showed you earlier the balloon, this is actually technically has radioactive materials in it because I exhaled in it. When I blew the balloon, I said, and I exhaled. Every time we breathe in some radon, and then I exhaled, and some of those got trapped in the balloon. So technically we do have radioactive atoms here in the air that we breathe. And of course, region to region, place to place, sometimes when with radon, home to home, there's variation. So we always have variation in the amount of radiation we get from natural environment. But on average, we get 3 millisieverts of radiation from the environment. That's living on Earth. On average, we get another 3 millisieverts from medical procedures. And a lot of us are getting X-ray exams, CT scans, and so forth. On average, that contributes another 3 millisieverts. 30 years ago, that was less than 1 millisievert, but now it's close to 3 millisieverts. Because the technology has advanced, so we're using that technology more. So total, on average, 3 millisieverts from the environment and 3 millisieverts from medical exposures. That gives us 6 millisieverts average annual dose to a person in the United States. Individual doses can vary. So many factors can influence your individual dose. If you smoke, the dose to your lung is actually quite significant, radiation dose, because of the radioactive material that's in tobacco. So smoking increases your radiation dose to your lungs. If you live at high elevation, say Denver, Colorado, you get a higher dose from cosmic radiation than if you live near the coastline. So where you live makes a difference. If you share a bed with someone, with your spouse or a partner, remember our bodies contain radioactive material and we actually measure radiation coming out of our bodies. We irradiate all the time. So when you're sitting next to someone, also you're irradiating each other. So obviously those who share a bed, they get a little extra radiation dose just because they don't sleep alone. So these factors, now that's a small factor, but there are these other factors, smoking, high elevation, and also other activities that would increase your individual dose. In this chart, you see some of the typical doses associated with some of common activities like air travel, chest x-rays, CT scans in units of millisieverts compared to what we get from our natural background. Now the frequency of these activities like air travel or medical procedure would impact your total dose as an individual. So even though our average is about 6 millisieverts, as individuals, your individual dose could vary and could be actually much higher in any given year. Now we talked about medical procedures, and in the chart I showed you doses for medical procedures. Now this does not mean that we should avoid medical procedures like CT scans because they have a clear benefit for us. Doctors, the imaging studies provide valuable information to our doctors to make diagnoses. So that's a clear benefit to us. So it's important to consider the risks and benefits of any procedure or activity that exposes us to ionizing radiation. As we discussed in the previous segment, radioactive decay is a process in which a radioactive atom spontaneously gives off energy in the form of ray or particles to reach a more stable state. Now this process that we call radioactive decay can also be called disintegration, transition, transformation. They all essentially mean the same thing. But what's important to remember and distinguish between radioactive material that contains radioactive atoms and the radiation that it emits. There are 3 types of radiation given off by radioactive atoms: alpha particles, beta particles, or gamma rays. Radioactive atoms may give off one or more of these types of radiation when they go through radioactive decay to reach a more stable state. In other words, a radioactive atom may give off an alpha particle and a gamma ray, or they may give off a beta particle and a gamma ray, or just an alpha particle. It just depends. Each type of radiation, alpha, beta, or gamma, has different properties that would affect how we can detect it and how it can potentially affect us. Alpha particles are subatomic particles, and they're actually pretty bulky. They don't travel very far in space because they bump into other atoms. The range of alpha particles in air is up to 1 inch, and we can shield them very easily. They can be blocked by a piece of paper. That means that alpha particles don't really present an external hazard to us. As long as alpha particles are outside of our body, they can penetrate through clothing and they can penetrate through the external layer of skin. So they don't harm us as long as they're outside. But they're a serious internal hazard if we internalize them. They come inside our body, then alpha particles can damage our cells. So it's an internal hazard, not an external hazard. Beta particles, they're also particles, not rays. They're very similar to electrons. And these have a longer range. They can go up to several feet in air. And it would take maybe an inch of plastic or so to block beta particles. Many of them can penetrate a layer of clothing. If they're on skin, they can cause skin burns. So beta particles represent an external hazard on the skin because they can penetrate the outer layer of skin, but also internal hazard. Gamma rays have a long range. They can go many yards in air, and it takes an inch or more of lead, several inches of lead, to block them completely. And they're also, of course, an external hazard because they can penetrate through material, they can penetrate through clothing, they will penetrate through plastic. And we'll talk later about how first responders need to be aware because their protective clothing won't protect them against penetrating gamma rays. It will take lead to block those. But they also can be an internal hazard. They're external hazard, obviously, but if we ingest or inhale radioactive material that emits gamma rays, they could be exposing us to radiation from the inside. Now, detecting and differentiating alpha particles, beta particles, and gamma rays is actually fairly easy if you have the right instrumentation. I'm going to demonstrate that to you. This particular instrument is a Geiger-Müller instrument, GM probe. This is a pancake style of instrument. And this is a very versatile equipment and it's commonly used, and there are many different manufacturers that make these. And it can detect all three types of radiation, alpha, beta, and gamma. It is designed for surface contamination for beta particles. But as I said, it can detect all three forms of radiation. And there are more specialized equipment too. I have one detector here that's specialized for detection of alpha particles. And when I want to demonstrate alpha particles, I'll use this particular instrument. So let's begin. I have some check sources too. These sources have very small quantity of radioactive materials that are fixed to the surface so they don't come off. And I have here to demonstrate to you. I'm going to start with alpha particles. And actually for the source of alpha particles, what I have here is americium-241. Americium-241 is a man-made radionuclide, so it doesn't happen naturally in nature. We don't find it naturally. It's man-made radionuclide. It's commonly used in household smoke detectors. The particular piece that I have here actually came from a household smoke detector. Now you'll wonder, why do we have americium-241 in a smoke detector? The reason it's there is that americium-241 gives us alpha particles. And these alpha particles ionize air molecules inside the smoke detector. And those create a small current, electrical current. So when smoke enters into the smoke detector, smoke particles attached to these charged particles and disrupt the current. That will set off the alarm. And it's a very sensitive instrument. So we have this americium-241 here. And I said we can detect them with both of these, but I'm going to use this particular instrument. And remember, alpha particles have a short range in air, and they can be stopped easily with a piece of paper, so we're going to see if that's true. Okay. So there's alpha particles being emitted here. See, I can't see it here, but if I put it right on top, now if I move up the detector a little bit, so I'm about an inch off, then I can no longer see it, because alpha particles have this limited range in air. They can be stopped in air like that. And now let's see if I put it right on top like that, you hear the counts. And when I put the paper on top of it, and right on top, nothing. So I slip the paper out just like that. So this piece of paper can stop alpha particles. And so they're easily shielded. And what that means is that alpha particles are not an external hazard. What do I mean by that? It means that, first of all, if you have a lot of alpha particles here, they can't reach us, so they have a very short range in air. If we have it in our clothes, they can't penetrate our clothing. And if they're on our skin, they can't penetrate the dead layer of skin. But they are, of course, a hazard if we internalize them and get them inside our bodies. So now I'm going to demonstrate beta particle, and we're going to use strontium-90 for a beta particle source. So you can see it has a higher range than alpha particles because I can still see it. And this piece of paper shouldn't do much. Strontium-90 has a pretty energetic beta particle, so we go right through paper. But now I can block it with a piece of plastic. Here, plastic shield. Here, you can see it here. So as I put the plastic right between the source and the detector, the counts are gone. So this is an effective shield for beta particles. So beta particles do present an external hazard because they, even though clothing can offer some protection, some of the energetic beta particles can go through clothing, but certainly if they're on the skin, they can go through the outer layer of skin and cause skin burns, and they're also an internal hazard. Now, let's move on to gamma rays, and the source we have here is cesium-137. Of course, the cesium. Now, to block cesium, it takes lead to block it. I have 2 sheets of lead. It comes maybe to less than ½ an inch. And let's see if I can hold this and do it. I'll put it on top like that. So I put this. Okay. So it's not all gone. It cuts it. But that's the effect of lead. So it takes lead to shield gamma rays. Gamma rays are obviously an external hazard because, for example, first responders, if they show up on a scene and their protective clothing cannot stop penetrating gamma rays, it will go right through that. So it's an external hazard that needs special attention. Another feature of each radionuclide is its half-life. That is the length of time it takes for half of the radioactive atoms in a population of radionuclides to decay. And I'll show it to you in an example. Imagine we have 100 radioactive atoms sitting here, and after one half-life, half of them would decay to a more stable state, and we will have 50 left. After another half-life, we would have 25. And after another half-life, we would have 12, and then 6, and then 3, and then 1, and eventually all of the radioactive atoms that we started with have decayed to a more stable state. So a half-life. And each radionuclide has its own specific half-life. And a good rule of thumb for every radionuclide is that after 7 half-lives, less than 1%, the original number, are still around. And this half-life can range from microseconds to billions of years. So the half-life varies depending on radionuclide. Some have very short half-lives, microseconds, and some have very long half-lives measured in billions of years. To give you a couple of examples, most radionuclides used in nuclear medicine have short half-lives because we don't want them in the patient for too long. Technetium-99 is the most common radionuclide used in imaging studies. That has a half-life of 6 hours. So one feature of radionuclides with short half-life is that when we talk about environmental contamination, if you have an event, an incident that involved contaminating an area or a room, but the contaminant has a short half-life, that means it will decay really quickly and go away. So something that has a 6-hour half-life, after just 24 hours, more than 90% of it is gone. On the other hand, uranium has an extremely long half-life. The half-life of uranium-238 is 4.5 billion years. Remember, that's a primordial radionuclide that's been part of the Earth's crust. It's in our soil and rock. So we still have plenty of it around, and in fact, if you take a soil sample from your backyard, you're going to find uranium-238 in there. Now, before we leave the subject of radioactive decay, one last point to make is that some radionuclides need to go through a series of transformation before they reach a stable state. It means more than one radioactive decay process through a series of steps. And again, uranium we were just talking about is a good example of that because it goes through a series of transformation before we reach a stable state. It starts with uranium, goes through thorium, radium, then radon, bismuth, and then ultimately a stable lead. So an atom that starts as uranium finally ends up happy as a lead atom, but it takes it quite a long time sometimes. As a result of this natural process, all of these radioactive atoms are now part of our natural environment. Now, when we work with radiation, there are different types of measurements that we can make. Let's say we had a radioactive source here. You should know that when we talk about the amount of radioactivity or levels of radiation, they don't necessarily correspond to the size, weight, or volume of a radioactive source. We could have a small amount of radioactive material that gives us a lot of radiation, or we could have a large bulk of radioactive material that gives us a little bit of radiation. That's why it's important to make measurements, to know what we have and what we're dealing with. The three types of measurements that we can make is the amount of radioactivity, ambient radiation levels, and radiation dose. I'll tell you what that means. Here's a jar of this, pretend this is a jar of radioactive sample. So the first thing we want to know is, well, how much stuff is in here? How much radioactivity is in this sample? How many alpha particles, beta particles, or gamma rays are given off by this material? That's the amount of radioactivity. So that's one measurement. Then we want to know, okay, we have this radioactivity here. Radiation is coming out. What is the radiation levels here? That's the second type of measurement. Radiation levels, ambient radiation levels as a result of having an environment that has radioactive materials in it. The third and last type of measurement is that, okay, what if I was standing here? How much of that radiation would be absorbed by my body? So in other words, what would be the dose to my body and to me? That's the radiation dose. That's the third type of measurements that we can make. So we have this jar of radioactive material, and let's pretend it's a material that emits alpha particles only. Now, as a review from a previous segment, if this jar contained radioactive material that only emitted alpha particles, what could we measure with a detector outside the glass? None. That's right, because it would not penetrate the glass. If this was gamma emitting, we could, right? If it was gamma emitting, we could have a detector here and we could measure it. But if it's alpha, then we'd have to open the jar here, and of course this was a bigger thing. We would have a probe, we could put it in close contact with it and measure the alpha particles. But in terms of measuring the amount of radioactivity, it's always best to collect a sample. That's the best way to analyze it. But if we have portable instruments, we could make an estimate of the amount of radioactivity. Now, to report the amount of radioactivity, the unit we use is becquerel. Becquerel is the international unit of radioactivity, and it represents 1 radioactive decay per second. That's how it's based. We have an older unit of Curie that many people in the United States still use, and the unit of Curie is based on the activity in 1 gram of radium. So we relate radioactivity in any sample back to whatever the activity is in 1 gram of radium. They both measure the same thing, they're just on a different scale. Becquerel, 1 disintegration per second, is a very small unit, but a Curie is a larger unit. So because it's so large, it's common to see not Curie, but millicurie, or microcurie, or nanocurie. And becquerel, because it's such a small unit, of just 1 radioactivity per second, it's more common to see kilobecquerel, and megabecquerel, and gigabecquerel. Now, to give you just a perspective of what these numbers could mean, what if I were to offer you something and say, just something to eat, a snack, and I told you that this snack had 12 becquerels of radioactivity in it. And what that means is that this particular snack emits 12 radiation particles, and I'll be more specific, 11 beta particles and 1 gamma ray every second. So you hold the snack, 11 beta particles and 1 gamma ray every second. Would you eat that? I bet you would. What I'm talking about is a banana. Remember we talked about potassium-40 in banana? That's what it amounts to. An average sized banana would have 12 becquerel of activity, more or less, and some bananas are bigger than others, but have 12 becquerel of activity. And so if you ingest that, it would continue to decay or to go through the natural reactivity inside your body. But you wouldn't worry about that. We eat this every day. Some of us eat this every day. And if you had 2 bananas or 3 bananas and so forth, you don't worry about the amount of radioactivity in it. You worry about other things if you had so many bananas in one sitting. But you wouldn't worry about radioactivity because it's such a small amount for each of these 12 becquerel. So another way to gauge the unit of becquerel. Remember we mentioned we'd have potassium-40 in our bodies? Well, our bodies are different, they come in different sizes. But like an average size person, we measured the amount of potassium-40 in thousands of becquerel. Thousands of radioactive decay per second inside our bodies. And that's every second that we live. And that's only from potassium-40. We have carbon too, remember, in our bodies. So we measure natural radioactivity in our bodies in units of thousands of becquerel. Because if you just remember before I showed you the banana, you were hesitant about the banana. And that was only 12. So one reason I presented you this example is that you're not going to remember becquerel or curie. And you're not supposed to, because it's not your job. So if you ever encounter some measurement of radioactivity, some units, ask someone, because you're not required to know. Ask a radiation safety professional to explain that number to you and put it in perspective. Because then you can gauge, then you can put it in perspective. Oh, okay, that's how much that is compared to something that's more familiar to you. So now this is one type of measurements. Now we want to see if we have this radioactivity here, what would be the radiation levels over here? And again, every time we want to do that, we have to know what's the natural radiation levels in the environment, plus whatever is coming from that source. So that would be the ambient radiation levels. The units we use to express that are gray per hour or sieverts per hour, international units. And those are huge numbers. So again, it's more common to see nanogray per hour or microsieverts per hour. In the US, we use the units of Rankton or rem per hour. And again, those are big numbers. So we use millirem per hour or micro-Rankton per hour. Those are more common units. Now you notice we express them in terms of hour. So this would be like millisieverts per hour. And the way we use that information is that, okay, so radiation levels here, let's say, would be 1 millisieverts per hour. So if I were to stand here for 2 hours, 2 times 1, I would get approximately 2 millisieverts of dose. So that would be the dose that I would get. So a common unit of radiation dose would be the dose that we would get. Remember from a previous segment, we were talking about millisieverts, getting 3 millisieverts from natural background radiation on average. So millisieverts is a common radiation unit we would see, sieverts and millisieverts. And in the United States, we use rem and millirem as a unit of dose. And the conversion is fairly simple. 1 sievert equals 100 rem, and 1 rem equals 10 millisieverts. So I said there are different types of measurements we can make. There are also different types of instruments we could use. So let me show you some of these instruments. This is the instrument. This is the pancake probe. It's a portable instrument, and it's ideal for measuring or screening for contamination on surfaces, either a person or an object. This is ideal for that purpose, and it's a very common instrument. Another instrument is ionization chamber, and there are different models of this. The ones I have here are just one particular model, but there are different brands and models of all of these instrumentation. Ionization chamber is a very good instrument to measure ambient radiation levels. Geiger counters would give us an idea about whether the ambient radiation levels are high, low, and give us some measure. But to make a more accurate measurement, we would need to use an ionization chamber. There is also a specialized instrument to measure amount of activity inside a person. So when a person has been contaminated and it's got internal contamination, and these specialized instruments are called whole body counters, and they measure the activity inside a person. Hospitals also have instrumentation that they routinely use to monitor the amount of radioactive materials that are given to the patients. And of course, we have laboratory equipment. This is a very sensitive equipment, and we can measure the amount of radioactivity in environmental samples, like in soil, water, or air samples. And we also use them to measure the amount of radioactivity in clinical samples. Urine, for example, that we would collect from people. If someone is suspected of having some internal contamination, you can collect a urine sample, analyze it in laboratory. These are very sensitive instruments and can measure very small amounts of radioactivity. The last thing I want to leave you in this segment is that to get reliable and accurate measurements, we need to have both, the right instrument and the right operator. The instrument is only as good as the person using it. So it's important to provide hands-on training to anyone who's expected to use radiation detection equipment on their job or in response to an emergency. And lastly, it's important to maintain radiation detection equipment to ensure that they're working properly. Radiation is one of the best understood health hazards. We've been studying the effects of radiation for over 100 years. So we know quite a bit about how ionizing radiation interacts with living tissue. We know that at high doses, radiation can be lethal. We know that it can cause cancer. We know that it can cause harm to the fetus at various stages of pregnancy. And although we haven't seen it in humans, we know that radiation can cause hereditary effect in laboratory animals. But as with other toxin, it's the dose that makes the poison. You recall from a previous segment that we're exposed constantly to a certain amount of radiation from our natural environment. So every exposure is not expected to result in harm. It's the amount of exposure, it's how much radiation we're exposed to, is the dose that determines potential health outcomes. So how does radiation damage living tissue? Ionizing radiation can break bonds in molecules, any molecule. Inside the cell, it does the same thing. And as with other toxins, our genetic material, DNA, is the primary target. And radiation can damage DNA directly by interacting with the molecule or indirectly. And that means we have plenty of water molecules in our cells. So radiation will interact with water, break down our water molecules, produce free radicals, and then free radicals will damage our DNA. That's an indirect method. But that's how ionizing radiation can damage our cells. So what happens once a cell is irradiated and it's damaged, the DNA is damaged? Well, it can repair itself faithfully to how it was before the damage, so the cell is repaired and there's normal function, and the cell would go on. Another thing that can happen is that it could misrepair, repair it incorrectly, so the cell becomes an altered cell. And then that cell has potential eventually to perhaps turn into cancerous cell. There's that potential. Alternatively, after the cell is damaged, the cell can die. So cell death is the outcome. And actually that's not a bad thing, because if only a few cells die, then the function of that tissue is not impaired. And we don't have a potential for a misrepair cell to later on cause harm to us. But if there is a lot of damage, if the dose is high and there's a large number of cells that die, then that impairs the function of that organ. And that's not good. We get organ failure at that point. So these are the three outcomes. In addition to dose that we discussed, radiation dose, health effects of radiation also depend on dose rate. How fast is that dose delivered to the body? So if the same dose is delivered over an extended period of time, the effect would not be as severe as if the same dose were delivered all at once. It also depends what part of the body is irradiated. If the dose is delivered only to a portion of the body, the health effect is not as severe as if our whole body, the entire body, is exposed. There is also individual sensitivity. Children and young adults are more sensitive to late effects of radiation. They have growing tissue, dividing cells, and they have so many years ahead of them, lifespan ahead of them is long enough to allow for any potential cancer to develop later in life. So children and young adults are more sensitive to that. Also, among individuals of the same age, there's variation in individual sensitivity to radiation. Now, to get a general feel for the range of health effects that we might observe from a very high dose of radiation to a very low dose of radiation, let's consider three situations. If the dose of radiation is high, it's delivered to the whole body, and is given in a short amount of time, the potential likely outcome is death. The individual would die. That death can occur within a few days. If the dose is really high, it could happen within a few hours even. And it could take several weeks after a period of severe illness that includes internal bleeding and infections. Now, if the dose is moderate, individual would develop radiation sickness. The symptoms will appear, but that individual has a good chance to survive. And the chance of survival is better if prompt medical care is provided to the individual. For those who survive this moderate dose of radiation, there will be a higher than expected risk of cancer later in life. So their risk of cancer would be higher than what we expect from average person. If the dose of radiation is low, there will be no radiation sickness, there will be no immediate health effects, no symptoms, and likely there will be no observable health effect later in life either. But statistically, there will be a higher than average risk of developing cancer later in life. So they would carry that small risk of cancer throughout their life. If the dose is really, really low, then that small increase the risk of cancer is so low that we can't measure it, we can't even estimate it. So for all practical purposes, that risk is non-existent at that point. So regarding potential health effects of radiation, remember, that's all about dose, which needs to be evaluated in context. On this chart, you will see typical doses from common exposures, including air travel, chest X-ray or CT scan, compared to what we get from our natural background on an annual basis. You also see the 50% survival dose. That's a dose that would give us 50% chance of survival. The person will have a 50% chance of surviving radiation sickness, and that dose is 4,000 millisieverts. That's equivalent to getting 400 CT scans back to back, or 1,300 years of natural background radiation in one sitting. Now, I know these dose numbers can still be a little abstract, so let me show you in a different way what these doses would look like. Instead of millisieverts, you just use pinto beams as a unit of radiation. Just for those of you who like radiation units, and I do too, but for this, I'm going to equate one pinto beam to 10 microsieverts or 1 millirem. So a pinto beam is 10 microsieverts or 1 millirem, but I'm not going to talk about dose anymore. I'm going to talk about pinto beams. Remember from previous segments, we get exposed to a certain amount of radiation from our natural background every year and so on. That equals to 300 pinto beams, and I put it in this jar. So it's third full. This is the amount of radiation we receive from our natural environment on average every year. And remember that this dose we get it on a daily basis, so the rate is equal to about 1 pinto beam a day is what we get just from our natural environment. So in one of these days, you need to get a CT scan. And when you do, what you're going to receive is about this many pinto beans, about 1,000 pinto beans, CT, abdominal CT, let's say. So this is about 3 times this. So it's 3 years worth of getting natural background radiation in one CT. And remember, you get a benefit from this. So don't forget that you receive a benefit from this dose. So let's not overlook that part. If you have to get a second test, of course you get a second one and so on. But this is part of our daily lives. This is what we do and what we get every day. So at what point are we going to see any effect that we can observe clinical, in a person that receives radiation or pinto beams? Okay, so this is the amount here. This is how many pinto beans we need to start seeing something in a person. The person who receives this many pinto beans still would not show radiation sickness, would not have any symptoms, would not feel any different. But if we took a blood sample from this person, we're going to see decreased levels of lymphocytes and platelets in this person. And that would be temporary. The person would recover on their own without any medication and would not know the difference. But there would be a temporary drop in blood counts. Now, this person will have a higher risk of cancer developing later in life. They will carry that risk with them. There will be a slight increase in cancer risk for this person, but there will be no clinical manifestation that can be observed. At what point are we going to see clinical? At what point are we going to see the effects of radiation exposure? That will be about 2 of these drugs. We're going to start getting into the territory of developing radiation sickness, about 2 of these drugs, but it's still not lethal. To get to the 50% survival dose, we need 10 of these drugs. So 10 of these drugs, if a person received 10 of these, will have a 50% chance of survival. The reason I wanted to show you this is that to illustrate the difference between doses in our daily lives that we're exposed to and the type of doses that can actually do us harm. Because we can measure radiation and because we can understand its health effects, we can work safely around it. And also, we can take practical measures to limit our radiation exposure. And I'm going to talk about those in a different segment. There are 3 basic principles in radiation safety. These are time, distance, and shielding. Time simply refers to the amount of time you spend near a radioactive source. Well, naturally, you want to minimize that. So if I'm working in a radiation area where radiation levels are elevated, I want to get my work done as quickly as I can, and then I want to leave the area. There's no more reason for me to stay there longer. Imagine a day at the beach. If you're out in the sun the entire day, you may get sunburn. But if you're there only for a brief period of time, you won't. So the amount of time you're out there makes a difference. Distance refers to the distance between you and a radioactive source, the radioactive area. And you want to maximize that to the extent you can. So let's say that if I'm working here and making a demonstration, these are radioactive sources here. When I'm done, I want to put the sources away or move myself away and increase my distance. And you can imagine maybe sitting next to a fireplace. You're sitting next to a fireplace close to it, and you feel the heat and you're uncomfortable. So you move to the other side of the room. So as you move, the heat intensity decreases. And that works exactly the same way. Radiation intensity decreases as you move away. The third principle is shielding. And shielding means putting a barrier, some shield between yourself and radioactive source. In a previous segment, we demonstrated how we use different material, plastic or piece of paper or lead, between the source and the detector to shield it. Now, it's not always that easy because radioactive sources may not be that small to be easily shielded. For example, first responders may report to a scene where there's been an accident and there's radioactive material, but they can't easily shield the scene. So they would deploy the principle of time and try to decrease their time they spend in the scene. But let's say for people, when we have widespread contamination in the environment, they can seek shelter inside a building that would offer them protection. Or let's say a surgeon who's operating on an injured individual, and the surgeon removes a piece of shrapnel, and it happens to be radioactive. You can put it in a lead container and shield the staff from the source. That's shielding. There's one acronym that I'd like you to remember. That's ALARA. Stands for as low as reasonably achievable. That's the guiding principle for controlling exposures to ionizing radiation. And what that means is that even if the dose is small, if receiving that dose doesn't offer you or anybody else any direct benefits, you should avoid it. To give you an example, these sources that I have here to make demonstrations, I don't keep them in my office right next to me where I sit. Even though they're very small doses, and even if I did that, it didn't amount to much, but there is no reason for me to do that. So when I'm not using them, I'm not sitting right next to them. That's the philosophy of radiation protection, as low as reasonably achievable. Decontamination is just a big word for washing or getting contamination off your body or an object. Understanding a couple of concepts are really important to the subject of contamination. So I want to review those with you. It's important to distinguish radioactive material from the radiation that they emit. Those two are different things. And it's also important to differentiate between exposure and contamination. So let's come back to this jar, and let's say that we have some radioactive material in this jar that emits gamma rays. So you remember the gamma rays would go through the glass. So I have the radioactive material here contained in the jar, but radiation that it emits would leave the jar through the glass and will come right at me at the speed of light, right? Okay, so I'm being exposed to the radiation. I'm being exposed to radiation that this material emits, but I'm not in contact with the radioactive material because radioactive material is contained here. I'm just being exposed to the radiation that it emits. So if I were to leave the room right here, I won't carry anything with me because radiation comes at me at the speed of light, does what it does, and it's gone. I leave the room, I'm not carrying anything with me. This is a lot like getting a CT scan or an X-ray. Get exposed to radiation and you go, you're not carrying anything with you. Now, if I were to open this jar and stick my finger in it, now this is contamination. Because now I've got the radioactive material on my finger. So contamination is when radioactive material is somewhere that it shouldn't be. It's not supposed to be. It was not supposed to be on my finger. So that's contamination. And now that my finger is contaminated, say I didn't know that, I don't know, so I go ahead and touch my hand here, and I touch my clothes. So my clothing becomes contaminated, and my skin becomes contaminated. And this is called external contamination, the contamination that you have external to your body, either on skin or clothing, external contamination. And when you're contaminated, guess what? You're also being exposed, right? Because radioactive material in the jar emits radiation. Radioactive material on your skin emits radiation too. So right now I'm being exposed also. I'm contaminated. And if I were to leave the area, I'm carrying that contamination with me. I'm also being radiated as I go. So this is different than just a simple exposure. And also, maybe if I don't wash my hands and go eat a sandwich, or if I touch my face and this material gets inside me, it becomes internal contamination. So when radioactive material is inside your body, that's called internal contamination. If it's outside your body, external contamination. The way we internalize contamination is through ingestion, eating, breathing radioactive material, or if I had an open wound and got contaminated, it would enter my bloodstream in that manner. And internal contamination is a health risk. It's something we want to avoid. And as you can tell, most of the times internal contamination starts from external contamination. So if you can manage to control external contamination, we can also help minimize the risk of internal contamination. Now let me ask you a trick question. In the United States, on average, we have 60,000 nuclear medicine procedures that take place every day. That's a daily average. Approximately 60,000 patients receive nuclear medicine procedures. These are cardiac stress tests, thyroid scans, or other imaging studies that involve introducing radioactive material into the patient. So the question is, would we call these patients internally contaminated? Now, if I hadn't made this a trick question, you'd probably say yes. But the answer is no, because radioactive material is supposed to be in their bodies. It was intended to be in their bodies so we can do the imaging study. Definition of contamination is when radioactive material is somewhere that it's not supposed to be. So we don't call those patients internally contaminated. But the patients themselves, when they leave the hospital, there can be a source of contamination themselves, because that radioactive material will leave their body through their sweat and urine, for example, and they receive instructions on how to control and manage that for a few days until the material gradually leaves their body. Now you can tell that nuclear medicine procedures are different from other imaging studies using X-rays or CT scans, because in those imaging studies we're only exposed to radiation, right? We're only exposed to X-rays or CT scans. There's no radioactivity involved, and there's no radioactive materials involved in those tests. Let's do a quick review. External contamination is unwanted radioactive material on your skin or clothing. Internal contamination is unwanted radioactive material inside your body. When there is elevated radiation levels in the area, you've been exposed to radiation. When you're contaminated, remember, when you're contaminated, you're also being exposed to radiation. But it is possible to be just exposed and not contaminated. It's very important to distinguish the difference between exposure and contamination. Let's talk about internal contamination. And if someone were to internalize some material, end up with internal contamination, what happens then? How long does the contamination stay inside the body? Well, there are two ways that the body would get rid of internal contamination. And how long it takes, it depends entirely on the radionuclide and also the metabolism of the person. The first mechanism when radioactive material decreases in the body is through physical radioactive decay. Just like radioactive material, we talk about half-life. And just this radioactive material sitting on the shelf, radiation levels would decrease as a function of time, depending on the half-life of the radionuclide. Well, the same thing would happen if that material is inside my body. It would still decay according to its half-life, and radiation levels will decrease with time. Another way is through biological processes and my metabolism. And it would leave my body, be excreted, because it would be treated like any other chemicals or elements that are in the body, depending on the solubility and the compound. So we have a biological process and a physical process where radioactivity levels would decrease. Of course, the physical process depends on the physical half-life of the radionuclide that we talked about. Biological process depends on the biological half-life of the radionuclide. Biological half-life refers to the amount of time it takes for half of the radioactive material in my body to leave my body. That's my biological half-life. Sometimes biological half-life is much faster than the physical. I'll give you an example. Cesium-137 has a half-life of 30 years. So if I had Cesium-137 in my body and my body didn't do anything to it, it would sit there for decades. But the biological half-life of cesium-137 is about 3 months. It varies from people to people. But roughly 2 or 3 months is the biological half-life. So it will leave my body through urine much faster.